Hello. Hello. Thank you, everyone. And thank you all for coming here today for our first panel discussion with Nanoscience Society and the Physics Society here at Cambridge. I'm Tara, for those of you that don't know me. And yeah, thank you all for coming here today. And today we're going to be talking about the future of quantum computing with our four guest speakers and our four panelists. So our first speaker is Fernando. Fernando leads Quantum Motion Technologies with the quantum hardware team, and he focuses on silicon-based quantum computing. He has a PhD with Cambridge and his research has over 50 publications and 5 patents focusing on quantum computing, benefiting both academia and industry. Our next speaker is Dr. Olivia Crawford, who is a senior quantum scientist at Riverlane, and she joined Riverlane as a scientist in 2018. Since then, she has worked on various aspects of quantum computing, from algorithms to error correction, and collaborated with external partners such as quantum hardware developers. Prior to Riverlane, Ophelia also completed her PhD on computational and theoretical geophysics, which is very interesting, I think. Following that, then, we have Federico Martins, who's also the group leader of Hitachi Quantum Computing. Federico's research activities have mostly centered on the physics and nano devices at Hitachi, and in particular on giving a direct and local understanding of the significant number of fundamental phenomena through experiments dealing with electron quantum interfaces and correlations, including quantum blockade and the quantum Hall regime. I know some people were doing the quantum Hall regime today here. And then finally, we have Dr. Stephen Herbert, who is the head of the quantum algorithms at Quantinuum. Stephen has led the quantum algorithms team at Quantinuum's Cambridge office, with a particular focus on quantum algorithms for classical computational problems, including quantum Monte Carlo integration, quantum topological data analysis, and quantum optimization. So thank you all for being here today and coming to speak with us about quantum computing. So we had a survey given out to everyone about 2 weeks ago now, and we got a lot of questions. So we narrowed it down into kind of a select few. And one of the main ones that was really kind of coming up at the start was to do with the challenges we currently face. So they're not a very commonplace technology at the moment, and a lot of people were kind of wondering, could we elaborate on the challenges we face as we are trying to build a quantum computer, and in terms of a larger scale, are they very scalable? So Federico, do you want to give a go?
Yeah. Is it working? Yeah. Well, thank you for inviting me to come and talk with everyone about this. It's a very interesting subject, I think. So quantum computation, it's a vision, it's a goal that we all want to achieve. Okay, it's a concept, and it's a relatively recent concept that people started developing in the last 20 years or so, and only like in the last, I would say, like 10 years, we really had like sizable progress, and so as a vision, we don't. There's a lot of challenges that we are confronting today. So there's on one side, we don't know yet if we can build a quantum computer. So we're trying to figure it out if it's even possible to build a quantum computer. And on the other side is it useful? Can we, if we build a quantum computer, can we do anything useful with a quantum computer? And this is questions that maybe it's surprising for many people, but we don't know yet. So like the first thing is that we have to figure it out: is this going to happen? If it's going to happen, and if it happens, can we use it as a useful tool? Okay. Now, what we know is that we like to learn, and we know that quantum is possibly the quantum physics. It's possibly one of the most advanced theories that we have. And it would be very nice if we can use it somehow. So quantum computing uses these techniques. So and so we are learning on the way. Maybe one day someone is going to come and say, well, these principles are better being used in another concept. But for now, that's the best we have in terms of quantum. That's the best thing we can find is a quantum computing.
Okay, and I was kind of interested there in you said that we don't even know if we can build a quantum computer yet. So we kind of have two kind of sides here of hardware, people kind of working in the hardware, but we also have a lot of people kind of working in the software, like Ophelia and Stephen here. Ophelia, what do you kind of think about that? I mean, working on all these algorithms and all the error correction when we don't actually have the computers at the moment to work on them.
Yeah, that's. Oh, do I have to
I think you
press
have to
the button?
press it.
Is that better? No. I think if you. Oh, just press it once. Sorry. Hello. Oh yeah.
Hello. Hello. Hello.
Maybe this
Oh.
one. Now it's already.
Thanks. Yeah. So, as you said, it's certainly early days for kind of real hardware. They're still quite small. They're still quite prone to errors. But I think we're getting to this stage where the development of quantum hardware is progressing quite rapidly, I would say. We're seeing sort of milestones in lots of different technologies, different ways of realizing quantum computers. We're still quite far from them being able to do genuinely useful calculations, but they are progressing quite rapidly. And at the same time, work on the algorithm side of things, on the software side of things, is kind of bringing down what we need the quantum computer to reach. So we've kind of got the quantum computer line going up and the requirements line coming down. They're not crossing. They're still some distance away. But I think it is very useful to be now working on bringing that line down so that we know what we're aiming for, so that we can kind of start to have a reasonable understanding of what we're going to need in order to get towards actual, genuine, useful calculations.
That's a really good insight. Fernando, do you want to say something?
Yes, I would like to follow on what Ophelia just said, no? Trying to bring that crossing point between what the hardware can do and the algorithm requirements to a closer point in time, no? And to discuss a little bit this, maybe we can put the question a bit more in perspective, no? What are those challenges? And one of the primary challenges is to make hardware sufficiently or computationally efficient enough or computationally powerful enough. Where does the power of quantum computers come from? From a couple of items. One is how many quantum bits or computational quantum units that your hardware have, and how reliable are your qubits. And the perspective that is out there, the calculations tells us that we need, for the simplest algorithms, of the order of thousands of qubits, if not millions or billions, no? And where are we now with the most complex quantum computers out there? 50, 100, maybe the largest quoted value out there is from an American company on 400 and something qubits that we still yet to see if it works. So we are still far from useful quantum bits for algorithms, but I know that the work of my colleagues here is making an effort to bring those number of qubits lower than what they were originally theoretically predicted. From my perspective of a quantum hardware development, there is also a very important challenge which relates to material science. And I just came from lecturing at the material science department, so I think it's very appropriate to talk about this, that we need to improve the hardware, the materials that we use to make these qubits, to make them as identical as possible to each other. You know, your integrated circuits, your laptops have billions of transistors. and they operate almost identical to each other. And that's one of the reasons why you can get so much computing power out of a really small chip. Qubits are not way near that at the moment. Each qubit, it's an individual. It behaves completely different from the one next to it. And you need to characterize each one with their particular properties. We really need to solve the challenge of how to make qubits as equal and as reliable as possible to help in the scaling process.
Okay, no, that's a really insightful insight. And then there was speaking about the two lines, kind of going back to that, and how the kind of algorithm side line is kind of going down, and we're kind of reaching more into this kind of NISQ near-term kind of scale, near-term devices. Stephen, you work a lot with kind of algorithms on the side. Do you kind of take into account the kind of limitations of the hardware as you kind of do these algorithms?
Yeah, we have to, unfortunately. It'd be nice to have as many qubits as we want, and it'd be nice if the algorithms I prove, I could just put my theoretical results down and get my quantum computer out, and the two would just tie up. But really, yeah, I would just challenge the idea of NISQ a little bit. So, you know, it's a useful way of thinking about near-term quantum computers, but the idea that there's kind of either fault-tolerant quantum computers where we essentially can use the circuit model like we prove things with and abstract away everything, or we have, you know, we just have to do statistical analysis on pretty poor qubits, is, I think, something of a false dichotomy. Really, we're looking at resource engineering to get sort of any sort of near to medium term use out of quantum computers. We've got, you know, even if we're assuming there is some error correction, if we can save qubits, we save qubits. We can do it on a smaller quantum computer. If we can save gates, we save gates, whether it's NISQ or fault tolerant. I think, you know, in terms of where we're talking to generalist audience about NISQ, I think it is useful to think about, can we get a useful computational effect using pure physical qubits? So we've got some kind of post-classical result. I'd say that idea has taken a hammering. There's perhaps one or two areas of hope. Some data science type application, topological data analysis, is one which is still much debated, but I think is worth consideration. Potentially some condensed matter physics. I understand that chemistry is less likely. It's not my area, but there's kind of, you need the kind of lattice symmetry to have a chance of computing with physical qubits. But really, I think there is a rightful shift towards looking at error-corrected quantum computers and resource engineering for the early error-corrected era with algorithms. And I guess now I've got the mic, I guess I'll be sending it away. So I just wanted to unpack a little bit the assertion that we don't yet know whether we can build a quantum computer. And from a kind of computer scientist point of view, this, you know, gross oversimplification, this basically comes down to two things. We, you know, either the laws of quantum mechanics may fail, or there may be some engineering reason why we can't scale the technology, even though we don't really question the underlying physics. The laws of quantum mechanics failing would be an extremely interesting scientific result, and we do have to think of quantum computers as science experiments still. And actually, there's a reason to believe that would actually deliver us a more powerful computational paradigm, although, albeit one we don't really know how to tame at present. But on the other aspect, I think the more likely aspect, I detect there is kind of cautious optimism, growing confidence that we can scale quantum computers, that this engineering problem can be overcome. I think suppressing noise in 2-qubit gates is key to that, whether we look at kind of NISQ running or error-corrected running, that's critical, and there is, you know, very impressive progress on that front. So cautious optimism from the algorithm's point of view, I would say, but resource engineering is key if we're going to see useful quantum advantage in the near to medium term.
Thank you very much for that, Stephen. I suppose one of the questions that kept coming up as well a lot in the survey was, we're trying so hard to build a quantum computer. We have so many groups, research groups all around the world building a quantum computer. Why? What are the kind of advantages? What are the reasons that we are trying to build one? And it's kind of open to anyone if anyone wants to take it.
Well, can I just comment on one thing, is that about this NISQ problem. So NISQ is it's this intermediate stage of quantum computing. So one of the the big challenges is to find goals that can be useful to keep people motivated. You know, quantum computation is going to take time. Maybe 20, 30 years, 40 years, who knows? But we need to keep people motivated. Let me give you an example. We were just talking 1 second ago, like before the talk, is that the transistor we managed to have transistors because there was a product that saved the transistor, was the radio. People could use, could produce radios, and this was well, now it sounds silly, but the radio saved the transistor because there was a product. We could commercialize transistors to give time to transistors to develop to the quality we have now. Like before, transistors were big. Now we have nanometer scale transistors. You know, there was a long way to get to a final product, and that's going to happen with quantum computation. Now, are we going to have enough stamina to keep like 50 years of development without having a final product? And that's why NISQ was so exciting as a concept, is that, well, maybe we can make something already in the middle, on the way. That's just a comment I would like to do. Yeah. And let's see if we can find products, like something that can keep the excitement about this subject, because now it's kind of, people are excited, but let's see.
Yeah, no, that's kind of really interesting because, I mean, everyone here today is from an industry.
Yeah.
So we have Hitachi, we have Riverlane, we have Quantum Motion, and we have Quantinuum. So it's kind of interesting that you're mentioning that it's kind of a race that we need to keep people interested. We need to kind of keep it kind of going like that and kind of keep the funding coming as well. Is that kind of a limitation in kind of some ways, as in kind of getting funding is kind of...
It's not just funding, it's also people. Like, I mean, like another thing we will discuss, like we need engineers, we need people to come to our labs and work. We need people. We don't. So now one of the things we have, like people that are hiring, is that there's not enough people. We need engineers, we need quantum engineers to come to our labs to work that are able to work. Of course, there's like a lot of different tasks to develop a quantum computer, but we need people that are able to come to work with us. If students don't find it interesting, there's no one to go work on the subject. It's funding, but not just funding, it's interest in general.
Fernando, you wanted to...
Yes, follow up on your question, Tara, whether there is resources now to make this a reality. I think it's a very good moment for quantum computing. There's been a series of very successful results in the community over the recent years that makes us believe that this is possible. And because of that, governments, private companies, independent private institutions are investing heavily to make this a reality. This is now, no? But then as well, following up on what Federico was saying, this will not be sustained forever unless there are intermediate results to useful quantum computing. And useful quantum computing, really advantageous computing through quantum, could be years away still from us, no? So all of us, our duty, or partially our duty, is to find applications or intermediate uses of the research that we do to keep things going. This could be in the form of intermediate products, intermediate results that maintain the interest and the promise of what we are doing. Because, I mean, unless there are intermediate results or even intermediate elements that can be commercialized because they are useful, it will be difficult to maintain the support that the field has at this very moment in time, no?
Does anyone else have anything to comment on that?
Yeah, I think that, remind me if I'm wrong, but I think there was a question about government funding sort of within that. And yeah, I think it is very important. I think we are, if you're kind of an American-style libertarian, I don't think market forces are going to coalesce to fund quantum to the level it needs to be. So we're looking at kind of the huge American companies just kind of funding in-house programs out of their other profits, or we're looking at national governments, invest in quantum because it's seen as an important thing for the future, and I think it is, and I think it's important, that governments do continue to support quantum in that way. They are targeted with their funding. They are supporting those who have a chance of building the sector. But I'd say it's critical, and I'd say it's also important that it's not just seen as a national security matter or a kind of geopolitical matter. It is, there are, humanistic advantages. A lot of this is a long way off, but the world spends a lot of energy on computation. There is an opportunity to do computation a lot more efficiently. For example, there's several improvements in battery technology, pharmaceuticals, etc. And really to support it because it's the right thing to do, and because we need to build a quantum sector is what I'd like to see as the motivation, rather than this kind of fear, which I do appreciate is successful at shaking down governments, but perhaps not the only way.
Perhaps on the topic of government, I think it's a really nice time in the field for like genuinely mutually beneficial collaboration, in a sense, between government and industry. It's relatively early stage. As Stephen said, kind of the industry needs the government's support, but also the government wants to understand how to enable the future kind of ecosystem in the best way possible, and to understand the potential impacts of the technology. So it's maybe a very nice time for this kind of very useful relationship.
No, that was really insightful, all of you. And you mentioned there at the end, Ophelia, the kind of impacts this technology that could have, and that a lot of people should be aware of. Because often, I do a PhD in quantum technologies, and often whenever I tell anyone I do a PhD, like I'm in quantum technology, they just think I'm just going to blow up the world and everything's going to be destroyed. But that's not really the case, I don't think, and a lot of people have a kind of distorted view in their head. So and this is kind of open to everyone, what are the actual impacts that this technology could have?
Yeah, sorry, I was putting it in a slightly flippant way, really. But I mean, things which kind of catch the headlines, they are worth paying attention to, and I don't want to diminish those. But things like Shor's algorithm for factoring breaking cryptography is expected to be some way off, unless somebody knows something I don't. But one of the things we can do with quantum computers quite successfully is we can simulate quantum mechanical systems. So hence the attention to pharmaceuticals, battery technology, anything chemical or material based. Something I'm personally interested in is cracking the hard problem of how we can apply quantum computation to data science. There's been an explosion in big data. My background's in classical computing and data science. But conventionally we think of quantum computers as things which kind of don't handle big data well. They handle kind of small data, big compute, and kind of bridging that divide. I think there is something there. The focus on topological data analysis is one of the reasons for that. Focus on Monte Carlo integration is one of the reasons for that. And when we can unlock kind of, perhaps we're talking more like those intermediate size quantum computers, optimization, estimation, certain subroutines in machine learning. I'm loath to say quantum computing is going to kind of revolutionize machine learning piecemeal, because there is a lot of subtlety in what it's going to do, but it is going to speed up subroutines in machine learning workflows. So anything you use your computer for today, potentially there'll be some subroutine which could be sped up quantumly. And when we get to that stage, the quantum is the competitive way to do that. We hope the algorithms and the technology be mature enough to actually enable that. I think there's others on the panel who will also have a view on this, so I'll pass the mic.
I don't think I have any better ideas than you, Stephen. I think as Stephen said, using a quantum computer to model a quantum mechanical system is somewhere where it's kind of very easy to, at a high level, understand why the quantum computer might have an advantage there. We're thinking about computational chemistry calculations, pharmaceutical applications, materials applications. That's kind of one of the key areas of excitement and potential, I think. Stephen mentioned lots of other things too. I now can't remember exactly what, but
And
perhaps
I have
another one is potentially things along the lines of linear algebra type problems, maybe in the context of fluid dynamics.
And is this with further down the line or more kind of near-term devices?
I confess. So I think it's clear that the biggest value from quantum computers is going to come when they can run kind of the most general calculations. And for that, we're going to need some form of error correction. And so we're looking to kind of fault tolerance for those large scale, most general calculations. It would be wonderful if in the meantime we can kind of find some specific use cases that can be useful. I'm mostly thinking more towards the long-term fault tolerance when we can do these large-scale general calculations. Yeah.
So the kind of bigger impact won't be made really until further down the line, you would think.
Certainly the highest impact is going to be once we can do the biggest calculations. I think it's very difficult to say exactly what we might be able to achieve before then. Is my fence-sitting answer.
Yeah, I think it's been very well summarized by our two panelists here. Maybe what I can contribute to is a bit more near-term application, maybe more for the physicists that maybe here in the room or chemists. And it's something that at Quantum Motion we see as interesting near-term application, which is the simulation of the Hubbard model, for example. No, so quantum computers are indeed as well good quantum simulators. They can simulate themselves, and if that themselves mimics the Hamiltonian, say for example, of the Hubbard model, you can program your quantum computer with the different parameters of that Hamiltonian and solve it, find the ground states, eigenenergies, eigenstates. Particularly, for those of you that don't know the problem, the simulation of high temperature superconductors could be mapped onto this particular Hamiltonian. So we foresee that we've done a bit of a resource estimation of what that will take, and we believe it's within the domain of the NISQ era, no? That era of intermediate noisy quantum computers. And as such, we believe that it may allow us to better simulate those high temperature superconductors that have been in the news relatively recently, no? Unsuccessfully, no? I have to say.
I just wanted to pick up on something Ophelia said. So I think she hit the nail on the head with linear algebra. When I was equivocating about machine learning, I mean, really it comes down to linear algebra, subroutines, eigenvalue, singular value type, transformations, manipulations. But I think the fluid dynamics mention is actually very on point, because this is an area where, as I've understood it, the full-scale algorithms which are expected to deliver the most kind of impressive quantum advantage are, I think, generally recognized to be full-scale algorithms. But there are tensor network methods which may not deliver quantum advantage, but they are interesting experiments. They allow users to get their hands on the tools, which is very interesting to experimental scientists, for example, in fluid dynamics. And you can basically contract a tensor network on a quantum computer. It may not be something you couldn't do classically, but it's a fundamentally different computational technique. And that's really kind of a gateway algorithm, if you like, to use quantum and eventually deliver quantum advantage. And I think that kind of captures quite a lot of the way that algorithms are being thought about in this kind of NISQ to full-scale way. So, yeah, thanks to the mention of fluid dynamics.
Yeah, no, thank you, everyone. One kind of thing that we were talking about a while ago was that we're getting the line for the hardware going up, and all the experimentalists and all the amazing kind of results that we're getting recently, and we're getting kind of the needs of the kind of software kind of going down, and they're kind of about meeting, but that would require a lot of theoreticians working with a lot of kind of hardware experimentalists. And I think everyone here can comment on this, because we kind of have a mixture of two hardware, two kind of theory. Are we working together? Is that kind of happening now? Not necessarily all of you working in particular, but are there theoreticians working with the hardware people? Do you want to say?
So the answer is yes. So we are already doing some kind of algorithms actually in our labs. Some very simple algorithms. So one of the first things we have to do in our quantum computer is to correct for errors, and this is kind of algorithm already. So the first goal is to go from what people call a physical qubit, which is a noisy implementation of a qubit, to a logical qubit, which would be a qubit that would be much higher quality. And so the first thing you have to do, like one of the first goals we are trying to do, is to implement quantum error correction. And these are algorithms. So we are already doing some kind of algorithms in our labs. Now the question is how to go beyond that, right? It's like that's the big question, and that's where we are right now. It's how to go beyond the quantum error correction. How can we have a perpetual qubit, and how to go beyond that? Okay.
Perhaps building on the error correction thing, so that the kind of at Riverlane, so we don't build any qubits, but kind of the one line thing we say we do is develop the error correction stack. So thinking about how you go from those real physical qubits on the hardware, which are rapidly improving, will continue to improve, but will always be error prone. So how you go from those noisy qubits to the less noisy logical qubits, which you can then use to do large scale computation. So I think for that, kind of in order to get the best out of your error correction procedure, you need to understand the hardware, and it's exactly what the best procedures are, the best protocols are, the constraints, the trade-offs in different aspects very much depends on what technology you're using for the quantum computer, and even within that, different hardware has very different properties, strengths. So very much in kind of everything we do, we work a lot with hardware partners. So I would say it's kind of, I'm not sure I know a single hardware company that doesn't also interact with people thinking about the other side of things, either internally or externally, and vice versa. I think it's, in order to get the most out, you need to understand the constraints from both directions.
Yes, so answering your question, Tara, I think actually here we have a very good example of collaboration between experimentalists and theorists. So actually, Ophelia and myself wrote a joint article that thought about how a silicon-based quantum computing architecture may look like in the future, and then what kind of improvement we could run on that, or how could we use that particular hardware implementation in the most efficient way for a particular algorithm. So my answer to your question is that is really key, no, to have this collaboration between hardware specialists and theorists. From my perspective, no, I'm passionate about developing hardware, and I could literally just go about developing the technology, no? But necessarily that technology needs to have a clear end use. And talking to people like Ophelia here and other theorists and our algorithm team at Quantum Motion really allows us to put that hardware development into perspective. As in, we can start to understand if we were to develop this particular architecture with such connectivity and such specifications, what are the results that we expect to have out of this, no? So that's one way and of collaboration. So algorithms that are designed specifically for the hardware that is being developed. But I think there is another very important direction, which is that influenced by the theory side of things, the algorithm development side of the field, which is to influence hardware developers to try to push their limits, such as they modify so slightly their architectures within the realms of what is technologically possible, to get that extra bit of functionality that you would otherwise will not get to. No? So there needs to be to have a flow of information in the two directions and a strong and tight collaboration between the two realms of the field.
Yeah, I think those are all points I largely agree with. So just to sort of give the Continuum perspective, so the history of Continuum is that we were Cambridge Quantum, a software company based in Cambridge and a few other offices elsewhere, and Honeywell Quantum Solutions based in Colorado, and there was a merger. That was a business decision, but that was also a scientific decision, so we're now a full stack company. And I understand from my colleagues that that's been pretty well received, having the kind of access all the way up, all the way down to qubits and lasers, controlling qubits up to applications. For me, I kind of sit in the ivory tower at the top to a certain extent. And really, when I look at kind of the theorist picture, I mean, something to bear in mind is I prove theorems in the unitary model of computation, basically, which is, assuming closed quantum systems. And I prove these theorems for, asymptotic results, so infinitely big systems. So neither of these two things are true, right? The system isn't closed, it's open, and we care about finite problem sizes. And as soon as you're in that regime, then there's practicality comes in, however much we try to avoid it as theorists. And really, one way to look at this is whether you talk about error-corrected qubits or physical qubits, those are statistical objects, not deterministic objects. And there's a saying that you tend to assume everything's a Gaussian, and mathematicians think it's an empirically observed phenomenon, and experimentalists think it's a mathematical fact because of the central limit theorem. But really, noise, the statistical character of the noise, has a huge impact on your actual guarantees from an application point of view. And it's really only by going and doing that measurement on the qubits, basically, and measuring, not just kind of coarse numbers like 2-qubit gate fidelity, but exactly how those errors manifest, that you actually understand that statistical character of that computation. You can actually kind of squeeze that extra bit out. So I'd say, it's certainly important to pay attention to the hardware as a theorist when it comes to practical application and when it comes to actually designing useful algorithms.
Thank you very much for that, Stephen. And kind of speaking about the kind of hardware, and I think Ophelia mentioned that some types of qubits have their limitations and some have their advantages. And every time I go on New Scientist or wherever at the moment, and if I look up quantum computing, big companies like kind of IBM come up with their superconducting qubits, and they're the kind of one that's the kind of key one you hear. But there's actually a lot more different types of qubits. For example, Fernando with silicon qubits, and I'm kind of wondering your opinions on that. Is it just going to be this one qubit that just dominates them all, one type of qubit, or are we kind of going to use each one maybe differently for different applications?
Yes, that's a very good question. Which technology is going to be the winning technology, no? And the type of answer that you could give to that question is unclear, no? Is it going to be one or is it going to be several, no? I think it's very early days, no? And there is a very good phrase to describe where we are and what we could expect to figure out at this moment from one of the fathers of this field, Scott Aronson, that said that basically you have all these qubits out there. Some are better than others in particular aspects. But to decide now which one is going to make the cut is like going to nursery. You have a look at the kids that are running around, and then you decide at that point who's going to be, say, a basketball star. It's very early days, no? That's the message that we have there, no? From my perspective, no? And why I work on what I do, no? Which is silicon qubits. I struggle to see a future in which any form of computation is not done on a silicon chip. all the computing that we have out there, either a laptop, a car, a phone, whatever, you name it, no? Sooner or later, it's made its transition to silicon technology. And that's what I believe in, that eventually we will be able to make robust and reliable quantum computers out of technology that looks very much like a transistors that you have in your phones or in your computers. So that's what wakes me up every day. That's what makes me do the research that I do with a lot of passion, because I would like to see that future in which we still maintain all our computing done on silicon technology. There is a but. That is likely that that computer won't be on top of this table, won't be in your pocket, because necessarily the research that we do, the technology that we develop, it's done at ultra low temperatures. We are talking about 4 Kelvin and below, and typically millikelvin temperatures. So from my point of view, that computer, particularly if it's silicon or a solid state system, will very much be placed in a data center and a specialized location where you will have all the cooling technology and you will be accessing that computer remotely in the way that you do nowadays as well. When you do your complex calculations, you may already access data centers. So that may be the case in the future, that you will get your access to a quantum computer through the cloud, and that quantum computer will be at millikelvin temperatures or something like that.
Do you want to say something on that, Frederic?
Yeah, I can also comment. I agree with Fernando because we work in the same, more or less same area, so I have to agree with him. Yeah, we have the same approach. Let me just try not to be so so in forward of silicon type of qubits, in a sense that, you know, there's a criteria that we, like a list of criteria that we have to make a good quantum bit and make a quantum computer. Okay, we call it the Loss-Divincenzo criteria, and you know, you need to have a two-level system. You need to be able to initialize in one of the states. You need to be able to manipulate it. We need to have long coherence time, so you keep that level. If you want to manipulate, you still be able to manipulate for a long time, and then you need to repeat this many times. Okay, and then you will have a quantum computer that's all good. Now, silicon, I mean, yeah, as Fernando said, you know, I have it everywhere. You know, I have 1 billion more than billions of transistors in one single chip. You know, like, it's incredible how we can scale this thing up. So silicon is a very attractive idea, but to be you know, quite frank, we don't know yet. We don't know yet which is going to system that's going to win ultimately. Maybe there's other type of qubits that's going to come up and say, well, there's this new type, and it's actually much better than anyone else that ever thought. Some years ago, there was this topologically protected qubits. If we ever can make a topological qubit, we're out of the job with silicon qubits. You know, we just go out. It turns out not to be so clear cut. So let's see how the field builds up. You know, one thing I have to say is that I think if there is a qubit that's going to win, eventually I jump on that qubit. You know, like it's okay, it's fine. Like, I mean, we all jump on the same qubit. You know, it's fine, it's good. It's actually positive. If we ever decide which one is the winning qubit, we can all join forces on that qubit. But until now, we have to, you know, try and see which one goes better. So for now, the superconductor qubits is winning. So they have like they have like hundreds of qubits now, so which is very impressive and quite cool actually. But let's see how it progresses. You know, maybe difficult to scale it.
Yeah, so our public relations guy, Pete's in the crowd, so I have to grab the mic and fly the flag for ion traps, otherwise I'll get a memo tomorrow. But yeah, so as I also lecture in computer science here, and for the past 5 years, actually, I've set this exact question to my students as a discussion point, not because there's an objective answer, of course, but my view has changed a lot, and I think that's telling. So 5 years ago, I was of the view that superconducting was going to be the eminent technology because that's what everybody was doing, Google, IBM, etc. and because the surface code is particularly well mapped to what we believe we can do in terms of kind of the physical setup of those chips. And I used to say that Ion Trap's kind of the hipster choice. They're sort of the also-ran, but they've got a few interesting features. You can put them together in sort of different ways. And then there's a collection of other technologies. Whereas now it's a much flatter picture. So with Ion Traps, I think they're very interesting for near-term experiments. The high 2-qubit gate fidelities means they're very exciting to my experimentalist colleagues. There are, results suggesting topological phase of Ion Trap qubits as well, that is not fully explored, but that's a very exciting aspect as well. I think we need to still give a lot of respect to superconducting. That has been very heavily researched by a lot of very, very notable people who know what they're talking about. Silicon, I'm excited about as, the big data aspect, frankly. I want once there's quantum computer, I want them to be stamped out fast and put in a kind of quantum computing data center. And I think the existing technology around silicon is very exciting, and photonics is the genuine dark horse, and I'd be extremely keen to see a little bit more in terms of information in the public sphere. So it's a very nuanced picture. And one thing I think is quite telling is on the Cambridge Quantum side of Quantinuum, we have stayed hardware agnostic because we don't want to, whilst we fully support and we're very excited about our hardware colleagues, we do recognise it is a heterogeneous picture, and it's likely to remain that way for some time.
Perhaps, just firstly to echo what Fernando said, it's very early. We're still seeing, all these different technologies do different things. As Stephen said, seeing the different kind of pros and cons there. And to provide another example of how it's changing quite rapidly and how your perceptions of technologies can kind of change over time. I don't think anyone's mentioned neutral atoms yet. Some colleagues, there was a quantum error correction conference in Australia a few weeks ago, and some colleagues were there, and there were some neutral atom results presented there that were very exciting. They hadn't been in the literature yet, but it kind of showed that there'd been quite rapid development in that particular technology. So just as another example of, we are still very early. Things are changing very rapidly, getting better in different ways, and even kind of doing direct comparisons between technologies. It is quite difficult because there's no sort of single thing you can say you're aiming for right now.
Thank you all for that. I really like that.
Can I just add a comment? So I think Riverline is a good example. It seems like we are competing with different technologies. Not necessarily. Most of the times we are actually learning from different techniques. So like a lot of technology that was developed for superconducting qubits, we are now using in the silicon-based quantum computing. So a lot of these problems we share. So it's not always competing. We are learning. Okay.
Kind of like friends in the school that Fernando was kind of talking about. Cool. So I suppose now I'm going to open it up to everyone to see if anyone here has any questions. And for the best question, you can wait. I suppose the panelists can judge whose best question is which, but you can win my colouring book on the colouring adventures of Cube with the Cat Guys. So better ask some good questions. So if anyone has some question, please raise your hand. Yep.
So Ophelia, you started off talking about how you need engineers and researchers to work to actually. And Steve, you also spoke about how when you solve problems, you abstract them away. And I guess one of the things that is very different in quantum computing to classical sort of algorithms development is how high the bar of entry is, both for working in theory as well as working in experiment. There's not much you can do without at least a bachelor's degree. Whereas if we look at what's happening in I don't know, like artificial
That's a great question. You very nicely compare with people working on artificial intelligence domain. There's a large community there that's organized itself very well. Particularly, it's provided free material for people to learn and to upskill themselves in their own time, whether they are studying or doing something else. You can just go online and get yourself taught some key aspects of machine learning, artificial intelligence, you name it. The quantum computing community maybe is not yet that big, but we are starting to see that there's a necessity to do something very similar to that, which is to provide education to people in the form of face-to-face courses or even MOOCs, massive online open courses, to train themselves in their own time. No? The reason why this has not happened much, I think, is maybe boils down to the size of the field. We are not that many just yet, but since we are growing, you start to see much more of this. No? Nowadays, you can find online courses that will teach you specific aspects of quantum computing. You can take them as you study and prepare yourself, no, for entering the business. And there will be more of this. No? Actually, in Quantum Motion, we are preparing our own program for upskilling people from day one. Particularly, this is targeted to bachelor or master students, because we foresee that there is no anymore a necessity to have a PhD in quantum physics to get into this. No? It's not anymore the field of just a bunch of physicists. This is a global endeavor that requires engineers, electrical engineers, mechanical engineers, computer scientists, chemists, you name it. No? It's much more global. So that's going to happen, and eventually happens. As I said, I think nowadays the industry as well is much more welcoming to bringing people that may not have all the training, but the industry is ready to give you that training and upskill you such as you can start producing and be a very useful and contributing member to this field.
Thank you, Fernando. Does anyone else have a question? Yep. Does anyone want to give a try?
Perhaps on the first question, so just to check I understand, you're asking about kind of sort of as individual scientists reconciling kind of the desire to do scientific research with the fact that you're in a company and that has. So I would say for me personally, that's actually like kind of the ideal combination. I sort of like this kind of research that has direction and is driven towards wanting to get to kind of useful end applications. It obviously means you don't have total freedom, but I think that kind of balance actually for me is a big positive thing. I would say, I don't know if anyone wants to answer any of this.
Yeah, on the second part of the first question, I mean, the answer is you don't look for layman investors. You need informed investors who are going to go with you the steps of the way and have realistic expectations from the start. Otherwise, it's not going to work out. I didn't actually catch the second question. It's to do with cryptography.
I'm not familiar. I'm not familiar with that problem actually. So I don't know. Stephen, you know anything about this or?
Yeah, I'm not super familiar, but I mean, I'm familiar with the theory, with the experimental practice. There are results on QKD. Noise is, I mean, it's simpler to take into account noise in kind of information protocols than computational protocols, because you can kind of do something which is more closely analogous to what you do classically, but it is still the corrupting effect, which is going to lose your kind of quantum protection. But yeah, I think it's just a case of driving noise down, driving correction up, really. And there are results. I think Toshiba having around Cambridge, where they've got nice kind of benchmark results, but we're still at that stage, really, benchmark results, and yeah, proving longer distances, fewer repeaters, that kind of thing. But I think, yeah, I don't know if anybody else wants to add. I think that's perhaps all. I'm probably already spoken more than I'm qualified to say on that.
Thank you, Stephen, for that. Is there any other questions? Maybe someone in the Aldrich? Thanks, Aldrich.
So you refer more to the ethics of quantum computing and the yeah, and the honesty of the scientists and the people using it. I mean, I think it's like with any other technology. Technology can be used for good, can be used for bad. There are two sides of the coin. No, it's probably fair to say that everyone that's sitting here doing quantum computing are doing it for the will to deliver a useful technology, and by useful we mean that serves to improve our lives. No, I don't know. It's difficult to say whether an application will be developed in the future that doesn't serve that primary goal of a scientist. It could well be, no? I mean, we've seen in history there's been different ways in which technology development has gone, but I don't know. I think the community that we work in, it's very research-oriented with the mentality to deliver something, even though it becomes eventually a commercial product that can be useful and helpful. No? Mm-hmm.
Yeah, I mean, I think this is an unanswerable question, really. I mean, if you push a technology out into the wild, then it will be used in whatever way people use it. And you could have asked any any inventor back through time, the end result of what they do. But one thing our founder, Ilyas Khan, on the Cambridge Quantum side has been very active in is trying to build ethics into the quantum sector from the start, and trying to build cross-community support for kind of an ethical approach. Of course, that will only go so far. That's kind of this closed shop mentality we have to a certain extent at the moment, which we want to break down and become more open. But with it comes the risk that people can use the technology as they see fit, and those two things, go together really.
Thank you, Stephen. And then as a final question, does anyone want to ask? Yep.
So I guess the answer it's very different. It's really very different. So we use the analogy for computers because it's what we have, but the way it works and the way the conception and the algorithms, it's a total new different world. So even the problems that we can solve with the quantum computer are not the same type of problems, and that's the reason we say that a quantum computer is not going to replace a classical computer. So a quantum computer is much more like a calculator, a very good calculator, and can be used. So one of the big applications, like in principle, it can simulate the world. And the idea behind is that the quantum computer already uses the principles of quantum mechanics to make the calculation. That's like the fact it already has encoded, So this is already one of the basic ideas. You want to solve an equation, Schrodinger equation. You can write the Hamiltonian and you can try to solve that, and then you can even try with a classical computer to solve it. The problem is that it's extremely inefficient way of solving a problem. And then we understood from the very beginning of using quantum computer, we understood that problem was already very hard to solve with a classical computer. So we invented this new concept of saying, okay, let's use a computer that already has some things encoded, like some quantum physics already there, to use it to solve these problems. But then you have to redo everything. You have to redo the hardware itself, but you also have to redo the algorithm. So it's only the name stayed more or less the same. So we are opening a completely new field. It's a complete new field. There's nothing. I mean, you can do analogies, but that's what's fascinating in this quantum computing. Is that it's everything is new.
Perhaps just to sort of repeat things people have already said. So when we're thinking about quantum computers, in some length of time from now, when they are large and capable of doing useful calculations, these will, as everyone has said, be only useful for these specific types of calculations for which quantum computers are useful. And as was also said, these aren't going to be things that will be sitting around in every room, every computer room in a college or something. It will be sort of select users perhaps accessing large data centers for the specific problem they want to solve. Exactly what that access will look like in terms of any analogy to kind of existing interfaces to supercomputers or software, I think it's another thing. It's too early to say. In general, at the moment, when we think about access to a quantum computer, we're sort of several levels below those eventual end users. It kind of has to be a kind of lower level. So yeah, exactly how software and things will look at the very end when we get there, I think is difficult to say.
Okay. Do you want to go say something, Stephen?
Yeah, did you say this is the last?
Yeah.
Yeah, so I was just going to finish on the note of controversy and contradict. So, you know, one way to look at a quantum computer is it's nothing but a machine for multiplying together very, very large matrices. And so if you can refactor your classical workflow, so you've got something which is just a big matrix operation, then you can send it to the quantum computer. It's a little bit more complicated than that, but there is a way of thinking about quantum computation within classical workflows. And these two, you know, these 2 points of view are both complementary, both valid actually, but seem actually completely contradictory.
Okay. Thank you very much for all your time, guys, and being here with us today. And thank you, everyone, for coming as well and hearing everyone speak in your questions. I personally think the first question was amazing, so I'm going to give the book to the first question. And yeah, thank you all here. Thank you.